I'll introduce our work on Omni6DPose, a comprehensive benchmark for universal 6D object pose estimation and tracking. Omni6DPose primarily consists of three components. First off, it features a vast collection of pose-aligned objects. Next, it includes real-life videos specifically captured for 6D object pose estimation, which we refer to as ROPE. The third component is the physically based simulated data for training, dubbed SOAP. Together, these elements form an extensive, versatile dataset for the field of 6D pose estimation. The paper presents benchmarks conducted on this dataset for two distinct tasks: 6D object pose estimation and 6D object pose tracking. Previous 6D object pose estimation datasets were mainly divided into instance-level and category-level datasets. However, the previous instance-level and category-level datasets featured very small scales of instances or categories. Omni6DPose provides a larger scale of instances and categories, along with diverse materials, overcoming the previous constraints. There, we highlight the diverse and comprehensive nature of Omni6DPose. We cover 149 categories, showcasing materials ranging from transparent glass to metal, ensuring our models can handle real-world variability. Our dataset also includes 5,000 distinct objects, varying in size from small utensils to large furniture, indicated by our size distribution graph. This diversity in features is crucial for advancing 6D pose estimation and tracking technologies. This slide presents detailed statistics, emphasizing object symmetries and materials. We catalog objects ranging from non-symmetrical to continuous symmetries, material-wise. Our dataset encompasses diverse materials, including significant portions of transparent and specular objects, introducing advanced challenges. Here is a detailed comparison between our dataset and existing datasets. Our dataset, SOAP and ROPE, significantly surpasses previous ones with a remarkable increase in object categories and instances. Unlike other datasets, ours includes a substantial number of challenging objects made from transparent and specular materials, providing a more comprehensive benchmark for the 6D object pose estimation field. For our ROPE dataset collection and annotation, we implemented a highly precise and efficient workflow. Initially, we use a high-accuracy scanner to obtain detailed 3D models of objects. We then manually align these objects to the canonical space. Next, we capture videos with an RGBD camera. To annotate poses efficiently, we first apply structure from motion to determine camera relative poses within the video. Subsequently, we select keyframes using farthest point sampling and annotate to D3D pairs. Starting with these initial poses, we refine them through optimization and finalize with manual adjustments. This meticulous approach ensures our datasets high quality. These are some visualizations of the ROPE dataset. The large-scale dataset and diverse materials present new challenges, such as generalization and the ambiguity issue. To train the network, we generated a large-scale dataset, SOAP, using simulation methods. By employing spatially context-aware mixed reality techniques to generate RGB data, we have reduced the RGB sim-to-real gap. Additionally, by creating depth data through physical-based depth sensor simulation, we have minimized the geometry sim-to-real gap. These are some examples of SOAP, demonstrating the realism of our generated dataset. To address the challenges of this diverse, large-scale dataset, we developed a generative category-level 6D object pose estimation approach comprising three key elements. First, we employ semantic-aware feature extraction, merging semantic information from pre-trained DNOVita with geometric features from PointNet++. Then, we predicted object 6D pose using a diffusion-based model, addressing ambiguity. Finally, we resolved discrete symmetries through a novel clustering-based aggregation method. We've evaluated 5 previous category-level pose estimation methods. The upper figure illustrates their performance compared with our method, measured by the area under curve values of IOU accuracy and volume under surface values of pose accuracy. The lower figure demonstrates detailed pose accuracy over a joint range of rotation error and translation error thresholds. Here comes a grid of videos showing the performance of baselines and our method. The predicted poses and scales are annotated by RGB axes and gradient-colored boxes respectively. This table presents the performance of category-level object pose tracking algorithms. The category-level pose estimation methods appear to achieve relatively better outcomes, since they benefit from learning the category-level canonical space of objects within the SOAP dataset. We performed a series of ablation experiments on our method. The findings demonstrated the importance of every element in our method. As a conclusion, we present Omni6DPose, a comprehensive 6D object pose estimation dataset with extensive scale, diversity, and material variety. We also propose a real data collection pipeline and a simulation framework for generating synthetic data with low sin-to-real gaps. Moreover, thorough experiments suggest that the probabilistic framework with semantic feature from 2D foundation model is promising to address large-scale pose estimation challenges. For future works, extra categories and instances are expected to be added into our datasets. Additional benchmarking is still required in the field of the instance-level or reference-based object pose estimation. Apart from that, some downstream tasks, including object rearrangement and robot manipulation, are able to leverage a better model. And finally, the inference process of pose estimation and tracking has the potential to be further speeded up.